Alright, so my folks at home who are listening, we already finished our foldable. Here's what we did for the first 25 minutes of class. We're going to check our homework too. You can read, blah, blah, blah. This will be due very soon. Okay, so they know what we're doing now. We're going to put away our foldable, finish last thing you're writing. We're going to go over 10 and 12, okay? So, especially my people who are finishing writing units, I need to see those at the end of class because I know that there were some concerns about should we cancel units, are you sure you know what you're doing, and so forth. This should be on my under Unit 5 docs as well. And if you have like a sample that you finished up, like maybe Boyle's Law, follow that same template throughout the rest. So, here's number 10. This is the one I heard a lot of cries for help on. So this one actually had you do some extra percent yield and understanding how to read the question and think about what the end goal is. So student A and B from the same experiment. Okay, so they decomposed a compound to obtain a gas. So you can imagine later on where it says determine a reaction that they could have used. We can think of anything that would produce a gas. We'll get there in a second. Student A collects 5 liters of the gas at 25 degrees C. Automatically, you write degree C, what do you need to do? Convert to Kelvin. What is that actually? 298 Kelvin. Okay, so that's a volume and that's a temperature. Cool? So immediately take your temperature from Celsius to Kelvin. Don't forget, because then at the end you might forget when you plug in. What? It's 290. That is right. 273 plus 25? 273, 293, 280. Yeah, we're good. Student B collects volume of 4.85 liters and gas at 22 degrees Celsius. What's that in Kelvin? 295 Kelvin. Who has these givens written down for number 10? If you don't, write them down now. I promise you, I am modeling appropriate methods of solving. I'm not doing just for me. This is for you to give yourself a step up on how to approach a problem. Yeah.
You convert the liters to milliliters?
You don't need to. No, volume is okay in liters or in milliliters. Temperature must be in Kelvin. Pressure is really good in atmospheres, millimeters of mercury, kilopascals, torr. It's good with any pressure unit, especially if you have the same pressure on each side. There is one gas level we have to use atmospheres, and we're going to talk about that later today. Okay, so the theoretical yield of the reaction is 4.97 at STP. What does STP give me? Standard pressure to be what? 1 atmosphere, and standard temperature to be 273. Okay, so given the fact that 4.97 liters occurred at STP, I need to note the fact that I can't really compare these volumes across the board because they're not all at the same pressure and they're not all at the same temperature. Well, do I really know they're not at the same pressure? Did A and B really give me any information about that? No. So I wrote this down because it told me to, but do I really need to compare it? No. So I'm just going to put a slash there because I don't need that variable in my face. So what are the percent yields for each student? So going back to think about what percent yield is, what's percent yield? Actual yield over theoretical yield times 100. So if we know we're going to do that eventually, we already have the theoretical yield right here, right? So what do you think I'm going to have to do with each of these students? I should be able to take their volumes and divide it by the theoretical yield, but I can't do that right now because the gases are not considered at the same temperature. Because if they do a comparison across volumes, I need to have a constant variable, which is temperature. So this was under the Charles Law section, right?
Yeah.
Right? So guess what law is probably going to be used? Charles Law, right? So BT, this is a V, and this is a T, right? So we have V over T, or we have V1, T1, V2, T2. But here's the question. I don't have anything to solve for. Hey, what is this nonsense? No, I thought I wanted more stuff. I have so much stuff in science still. Bye. Okay. So I already have both V's and both T's. So what am I looking for? We're actually going to take this and convert it to the pressure that the actual yield that we should be getting. Because is this really a V we'll use? This one? No, it's going to be used here in our equation for theoretical yield. That's not the V that's going in the Charles Law. That's the V. That's the volume we're looking at as theoretical yield over here. That's why this was a little bit of a difficult setup. Because you're like, I have everything. What do I solve for? We're actually going to solve for V2. Because that V is not the V of our comparison. So V1, T1, these are our V1 and T1. Should not write that again. V2 is what I'm looking for because I'm basically taking this gas and converting it to its liters that it would take on at this temperature, at standard temperature. So, using this information for student A, what's my equation? What's my equation? V1 over T1 equals, okay, so that's Charles's Law, Virginia Tech. Okay, so I'm solving for what variable? V2, so how do I isolate V2? Cross multiply and divide, or that thing, or times both sides by T2. Why? Right, so this V2 needs to be isolated, so this guy's got to get out of the way, so I've got to multiply by T2 on both sides. That's the same situation of copy dot flop or cross multiply and divide. We will in the end cancel these out. V2 has been isolated. Whew, okay, so V2 is equal to what combination of variables? T2 times V1 over T1. This is your algebra, right? So now I'm going to plug everything in. I like to rewrite it because sometimes you might mistake what's on the numerator, what's on the denominator. So what's our T2? 273 Kelvin. Okay. What's my V1? This is the student A's original actual yield, but now we're just appropriating it to its standard temperature conditions over 298 Kelvin. Okay, what units cancel? Kelvin. What unit remains? Liters. And so that's our verification that we're in volume, we're in liters. Whew. We make sure that our volume is appropriate, or our unit is appropriate for volume. What's 273 times 5 over 298? 4.58. Okay, so now this makes sense. Actually, student A, once appropriated to the appropriate temperature of 273, they actually got 458 or 4.58 liters, whereas the theoretical yield was what? 4.97, because that's what it said. It said theoretical yield is 4.97. So how do I do percent yield? 4.58 liters divided by 4.97 liters times 100, which is, say again? 92.2%. Wonderful. So that's how you appropriate. Given a condition of 273, that's the volume, that's theoretical yield. This guy collected 5 liters of gas, but not really 5 liters because his was at a hotter temperature, right? What does a hotter temperature do to a gas's volume? Increases it. That's why this was the 5 liters that it was. Well, when we appropriated it, kind of rationed it down, or used our ratio and brought it down to the temperature of 273, so we could actually do a comparison, which is what we saw for here. The comparison is our actual yield at this. Now these can be compared because they are at the same temperature. Times 100, that 92.2% is the percent yield for student A. What would you do for student B? Same thing. I'm not doing it right now, okay? So question 12 is my next one. Yes? Most people had pretty good success on some of those others. Okay, so calculate the temperature of nitrogen gas if 2 liters of the gas at STP is subjected to a pressure of 920 millimeters of mercury. Okay, so what are the variables you guys wrote down for 12? The variables of interest. So this is calculate the temperature. Okay, calculate the temperature. That's our question of nitrogen gas if. So it says a volume here, 2 liters of the gas is subjected at STP. So here's how you have to read this question, okay? Calculate the temperature, that's our kind of question, and then if 2 liters of this gas is at STP. So whatever I write next to this is considered with this volume. So then it says at STP, well, what information does that really give me? a pressure of 1 atmosphere and a temperature of 273, right? So these things were given all together. So I'm going to label them all the same condition. So I'm just going to label them all 1s. You could label them all 2s if you wanted to, but these were given together. That's the hard part to see in this question. So V1, P1, and T1. Now, so calculate the temperature of nitrogen gas if 2 liters of the gas is subjected to a pressure of 920 millimeters of mercury. Pressure of 920 milliliters of mercury. This condition is talking about this temperature that we're looking for. So I'll label those both 2s. Oops, 2s. What do you notice I don't have another of? Say again? Another volume. So think about Gay-Lussac's law. Does it have volume in it? Does it ask me for volume? Not really. It's just saying, hey guys, I got 2 liters of this gas. Go me. That's kind of distracting, but if you think about it and it doesn't give you a second volume, you won't be using volume in your comparison. But you will use pressure, temperature, this pressure, and solve for this temperature. So I'm going to cross that out because I actually don't need it through calculation. So what's our gas law? P what? P1 over T1 equals P2 over T2. What am I solving for? T2. This is the one, everyone always has a hard time isolating a denominator because you want to figure out how to just do it real cheap and easy, but it's not cheap and easy. Either copy dot flop, which I'm not comfortable with because I didn't learn it that way. I learned cross multiply and divide. If you cross multiply, P1 times T2, those are multiplied by each other. I'm writing them down here. And you set it equal to the other cross multiplication, which is this guy. So you're cross multiplying. See, I'm writing that. And I'm just going to divide. Now that everything's multiplied, I can just divide by the variable I don't want. What do I not want? I don't want P1 here. I want to divide by that because I need to isolate T2, correct? Because that was my question. T2. So I'm going to divide by what? P1 on both sides. I know that over here it will cancel. T2 is remaining. Great. T2 is equal to P2 times T1 over P1. So what's my P2? 920 millimeters of mercury, right? Okay. What's my T1? Oh, for some reason I'm not writing K there. Okay. 273 Kelvin. All right. What's my P1? Right, so I already see some people's wheels turning. They're saying atmospheres here, but millimeters of mercury here. Those units will not cancel. So I have to choose one. I always like to just take my 1 atmosphere to whatever it can go to because I've memorized the relationships. 1 atmosphere is equal to 760 millimeters of mercury. And so knowing that now, I can cancel what? Millimeters of mercury, and I'm stuck with Kelvin, which is good because that's a temperature unit, so it kind of shows me I'm in the right place. And then, like 290 something. What's this answer? 2 what? 2 what? Okay, I was guesstimating. I'm ready. 330.5, and that would be. Let me see. Was it 290 dot or 920 dot? So. That should be 366, so 331 Kelvin, which is what Celsius? How do I get to Celsius? So this minus 273, which is 58. Sounds right. So that's why I've probably published on mine to get published mine in Celsius so you can see the relationship between the temperature variables. Okie dokie. Alright, so I'm going to pause for now. If you guys have some more questions on this specifically, I'll just denote that all units should be listed, which will help with making sure your units cancel. All Celsius should be converted to Kelvin, and I think that's really all your mishaps might really be. Okay? Yeah.
On number 10, I don't understand what it meant by like writing
Oh, the balanced chemical equation. So really, I just wanted to have you guys review equations. So what's a good example of any type of reaction that could produce a gas? Many times, which of the 5 types of reactions will produce a gas? Okay, combustion or decomposition. Those are the two big ones that will produce a gas. So what's a good example of combustion? Combustion of, we'll do butane. Great. Steve? C4, H10. Okay, so carbon with a butane. Butane means four carbons, 2 and plus 2. And combustion means to add oxygen, and combustion of a hydrocarbon always produces carbon dioxide and water, and then you can balance that, right? Balance would be 4, 5, I can't do that, so 8, 5, 13, so that's 13, so that's 2, and that's an 8, and that's a 10, okay. So, you have to double everything because of the oxygens being odd. How about a decomposition? Potassium what? Potassium chlorate. Okay, ClO3 produces. So, what do you memorize? Metal chlorate is decomposed to metal chlorides plus oxygen. So, the metal chloride in this case is potassium chloride, and that is a 1 and 1. That's where there's no subscripts, and oxygen, and then we balance it by. Wonderful. So that's just making sure you understand that gases don't come from nowhere. They're coming from the production of a gas through a reaction standpoint. And we will get to this more in depth probably Monday. Okay. So let me pause. We have one more gas law to go over, but I think that you need to finish up your simulation first, which will give you some context. So go ahead and open your laptop. Go to your simulation from yesterday. You want to finish working with the person that was with you. I also can come around and help those individuals with some more questions on the ones we've seen. Especially if you're like, oh my gosh, I thought I had this right and I don't know what I did wrong. I can look for mistakes. So do you guys remember where the simulation stuff was? No? Were you here? Oh, some people left me. Okay, that's right. So if you go to, well, there's my attendance. I was trying to take attendance. If you go to my website under, if you were not here yesterday, look up here now, okay? I'm going to show you this. Go to my website under Unit 5 Docs, under Honors Chem. And you scroll down to where it says Gas Law Simulation FET. There's a link that brings you directly to the simulation and this little activity worksheet. So the worksheet has the questions that delineate what to do, tells you how to manipulate variables, and the simulation looks like this. So when you pull up the simulation, it'll say like, oh, start me, start, and it'll download it and be like, whoa, alert, do you want to keep this file? Yes. And it's like, are you sure? Because Java's going to be like, hey, you want to update me? You're going to say, nah, later. Maybe. I already said later, so it's not going to prompt me to do that, but yours may. But it'll start the simulation, and then there's this little guy, and there's a little pump. Boom, put your gas in. You can close a container and mess with variables. Okay? Do your thing. Thank you. Don't shake it, just invert it. It's a lava lamp. Isn't that just satisfying? Yeah. Yeah.
How do you get them to like move on their own?
Say again?
How do they get them to move on their own?
Heat them up.
That's all.
It's density of the wax. It changes, and as it goes to the top, it cools down. It condenses. It falls back down. It
So
heats
that's
it
what
up.
happens naturally.
Yeah. It's, well, because there's a lamp underneath, a lava lamp.
Yeah.
Yeah.
How was science night?
Exhausting. I walked 9 miles. Definitely want to make sure you get to your practice with this. So listen to me. Listen to me. Shelby, what's a theory? What is a theory? Anybody at the table? When I'm trying to talk, you guys cannot be talking. Yes.
It is an educated guess regarding.
Educated guess is the phrase most people use for a hypothesis.
Oh, okay.
Yeah.
Theory is an explanation of how something.
So a pretty long-winded explanation of how something happens or works, observations that were made repeatedly. So we got, guys, we drop stuff. This is a law, right? Stuff falls, right? That's gravity. Point blank, that's a law. That theory's like, let me tell you about the theory of natural selection. Well, these got these desirable traits, and the environment selects against these animals that don't have that trait. Those that do get the trait, genetically, they mate, they make more babies, that trait survives. There's this long, expanded theory of natural selection, right? You learned about that in biology. Well, I got another one for you. It's called the theory that relates to gas characteristics and gas behavior, called the kinetic molecular theory. Okay? So you wrote down a wee bit about this on your reading guide. The kinetic refers to energy of motion. Molecular just means molecules. So it's a theory that talks about the movement of gases. Okay? And this theory describes ideally how gases exist. Okay, so here's my analogy. Close your eyes and imagine that ideal man or woman. Okay? Ideal man or woman. Okay, so let me tell you about mine. He makes my coffee in the morning. He does the laundry. Tells me I'm pretty. Yeah, what are some other characteristics about your ideal person? Huh? Oh, you must be that thing. Yeah, give me 1 second, okay? I got you. Okay. Any more? Come on, give me some characteristics. Come on. Kind. Smart and intelligent. Okay. Can cook. Okay, so we can probably rattle off 10 or 15 characteristics. But would one person have all those characteristics? We hope so. And it makes our life easier if we just assume they can have those characteristics, and we will find that ideal person. But we might have to compromise just a little bit. But we can still assume because it makes our life easier. Well, we always assume the ideal gases exist because it makes our math easier. Okay, we make these assumptions. So here's the characteristics of ideal gases. Jacob, I got you. I know that's going on. Okay, we assume ideal gases have no volume. We assume they are volumeless. Because when they're in a container, and we have a volume of the container, and let's say the volume of the container is 1 liter, what if I have to account for the volume that those little tiny specks of gas take up? Ain't nobody got time for that. Like, they're small. We're just going to assume they're volumeless. If not, I'm going to have to go, well, there's 6,000 million quadrillion gas particles in there, and that's going to take up about 0.25 liters, and I'm going to have to go back and calculate the volume of the container. But I don't have the time to do that, and we're really learning the basics here, okay? So I got you, Shelby. It's not going to explode. I got you, okay? So we assume that the space they take up is insignificant. But guess what? Real gases, can you contrast ideal to actually? They actually have volume. But we ignore that fact for our calculation purposes, because if not, our math gets really, really complex. And we're going for simple right now, okay? Another characteristic, we assume they're in constant random motion. Is that what you saw on your simulation? Yes, right? But actually, couldn't gas particles hang close to each other? Maybe travel as a pair? Maybe they could attract. What would make them attract to each other? But we call their love an attraction. Why would things become attracted to each other? IMFs, intermolecular forces, they exist, right? We can't just ignore that. So we assume they're constant random motion. They're not attracted to each other. They're not hanging out together. But actually, IMFs, I think that's all I need to say, they could very well start to attract and move non-randomly, which might impact our collisions. So this could impact collisions. What happens if we change collisions? Yeah, we start to change the pressure, and that may not be predictable. Okay. We assume, these are the assumptions you are writing down. Thank you. Not right now. Soon. That's not clear. I need this last button. Okay, so elastic collisions, what does that mean? Right, so it's like, you guys know those little things that like swing together and they bounce? Yeah. We're assuming that they are not losing energy and they're moving at the same speed no matter what. But friction, Sometimes things lose energy and lose steam with friction. So we will say real gases what? Lose energy due to friction. So they might end up slowing down over time, but we're going to try to not assume that, because then we got to account for lower pressure conditions, and the math gets more complicated. Our ideal gases, we assume a really simple formula. And then kinetic energy, and this is assumed for everything. Kinetic energy is proportional to Kelvin temperature. So guess what? We will always use Kelvin temperature because this is how it's defined. We define the kinetic energy inherent in a population of gas particles by the kinetic energy, or by the Kelvin temperature it's at. And since my people are distracted right here, I'm gonna have Jacob do me a quick favor. Jacob, if you could put your goggles on. Nice here. So here's what he's gonna do. He's gonna plant He's gonna plant just like this, and he's gonna immediately flip it upside down in the water. So really fast, okay? So you gotta just use this way so people can see. Can you flip it on here? Yeah, you're inverting the hole into the water. Where do you want to go? In the water, in the water, in the water, in the water! Woo! Okay, leave the extra hot plate off, thank you. I have one more, here it is. Oh, here it is. I'm still not done here. Here it is, going to light these candles. You have to stand on this side. That's the center here. Right here, you're gonna hold the candle. Hold the other. Alright, Meredith's going to light the candles. Light the candle. You got it. I believe in you.
We've only been trying to find somebody like.
Oh. Alright, I'm gonna light the candle. You know, I have to do this last year. And Meredith's not going to push this again, but she's gonna let it hang here. Hold it. Hold it. Yeah, you're welcome. What caused that? So Meredith didn't push it in there, right? You held it. No. Okay. So the pressure difference is, you know, the pressure's all around us. Between the flask and outside, added it and pushed it up into it. All right. So I still got like one more point here. Hold on. Hold on. Thank you. I didn't have some people do that because you guys would have thought I pushed it in there, and I certainly did not do that. It was the pressure's fault. Thank you. And so the pressure crushed the can as well. Yeah, so the pressure around us compressed the can because we allowed the gas not to be able to escape by smushing the hole into the water. Okay, so here's our last bit, and then we'll talk about ideal gas law. So we make these ideal assumptions, this attraction component we already referred to up here. If we assume they don't attract, it allows our math to stay easy, because if we assume they start to attract, they'll lower their number of collisions, and if you lower your number of collisions, what do? You decrease your pressure, and then you're like, crap, I gotta deal with the difference in pressure through a calculation, and we assume these theories to keep our generalizable assumptions true. So with this, there's something called the ideal gas law that correlates to all the behaviors that you've expressed here. The ideal gas law is PV equals nRT. Okay, so PV equals nRT. Write that down, and I'll keep going here because I have it on the next slide. What do you think P stands for? Pressure. Pressure. Pressure must, in this case, be established in atmospheres. V stands for volume, and it's going to have to be, in this case, established in liters. Absolutely. These are non-options here, okay? N is established in moles, and that's kind of an always thing. I'm going to skip R for a second. T must be established in Kelvin, always. It is temperature, but it's going to be established in Kelvin. So this is an R, and R's, that's not really a variable we have. It's actually a constant. It's called the gas law constant. Okay? That gas law constant is here. 0.0821 atmosphere liters per mole K. 0.0821 atmosphere liters per mole K. So, do you know why now the pressure must be in atmospheres? Because you have atmospheres in your unit of the constant. Why does temperature have to be in Kelvin? That way it cancels with this, and temperature always has to be in Kelvin, okay? How about volume? It must be in liters because the gas law constant has liters. And moles are moles, okay? This is the R value, and we'll use that a lot. Okay, so I'm going to do one of the ideal gas law problems from your worksheet, number 17. You guys got that out? So I'm doing 17, you guys will do 18 and 19. 17. So a student collects, I have 2 minutes, here we go. A student collects, oh, what do they collect? 425 milliliters. What is that? That is volume. Immediately, you know you can't have volume in this case, okay? Volume in milliliters. It has to be in, what is that in liters? 0.425. You're moving the decimal back. I'm only doing liters because I'm telling you right now this is an ideal gas law problem. Normally volume can be in milliliters. Totally. Of oxygen gas, it has a temperature of 24 Celsius, which you know is 293 Kelvin because you added 273 to that. Is that right? 297, thank you. 297 Kelvin. I like to believe you guys. At a pressure of 0.889 atmospheres. Okay, what's the question here? How many moles? Okay, so we're solving for what variable? N. We're solving for N, which is moles. We'll get to the second part in a second. All right, guys, notice I don't have 2 volumes, I don't have 2 temperatures, I don't have 2 pressures. We can't use any of those laws we've already learned. We have to use the ideal gas law. PV equals nRT. Don't we always know R? Because it's a constant. We know R. It's 0.0821 atmosphere times liters per moles times Kelvin. Okay, so which variable are we solving for? N. Isolate N. This is the same exact process. Identify the law. Done. Isolate N. Tell me what's up. Maybe. Hold on. Say again. Divide by RT. Why am I dividing by RT on both sides? To find N by itself. Right. To isolate N. So when these cancel over here, N equals P times V over RT. Plug them in, plug them in. What's P? 0.889. I'm sorry, I'm not really speeding through this, but I am a little bit. Sorry, guys. What's V? 0.425 liters. What's R? Atmosphere liters per mole. Okay, I'll finish this right now. I'll upload the video. So you guys have a good spring break. I'm asking for 17, 18, and 19, which all pertain to this. If you didn't finish your simulation, I'll take it Tuesday, just in case Java doesn't work. And work on some of that from set 14, because we don't have very much lots of gases. We have Graham's Law, Dalton's Law, 2 labs. We're done. So basically finish up some gas law stuff. Peace, get out of here. Thank you. I will finish this. Bye, guys. Have a good break.
Huh? For what? That's the least of my work. I have a history test.
You didn't check reading guide 14.
Not yet. Yeah.
Okay. Or yes, technically we went over it the other day.
Yeah, and I checked for it the day it was due. Okay. And then I went over it with you guys. I didn't take it up.
Yeah, I'm not
I didn't show you it.
That was I actually see it. Not right now. Oh, okay. You're good. Okay.
Thank
Have a great day.
But I'm not gonna be that well.
No, like all those people.
All the what? Hey, man.
Okay, I found my types of reaction lab. Should I put it in the absent box or the inbox?
Please don't put anything else in the absence box. Absence box is a holding container for people who are absent. Do not put anything in there. And if
Oh,
you're
it
trying to-
is? Because I
Yeah.
put like
I know,
put a
I
bunch
kept
of stuff
finding
in
stuff.
there.
If it turns from the end,
Uh-huh.
put it in the,
Oh, I thought it was like, put work in there if you're absent.
no.
Oh.
If you have an inbox, put it in the inbox. I'm finishing this problem. Talk to me. Thanks for being my assistant.
What is the ST?
STP?
Yeah, what is
Standard temperature and pressure. Standard temperature is what? No!
273.
273 Kelvin. That's standard conditions, yeah.
Yeah, that's room
That's room temperature standard
Yeah,
conditions.
here
273 Kelvin.
is-
And what's standard pressure?
1 So what is that font? Would that just be like?
That's like used as a comparison. A lot of times, like as a second temperature and a second pressure for like Charles's law or Boyle's law or combined gas law.
Oh, okay. So that'd be like one of the two.
Yes,
Okay.
yes. As I'm finishing this problem on this video, give me a second. Yeah, go ahead and start on the rest of those FRQs under Big Idea 6. Are you in leadership? No? Take it. I don't know. Oh yeah, I did yesterday. I did. Oh, but we use so many people's recycling bins. I didn't know who I had. Sir.